Good evening, and this video is about the friction lab. And I just want to do this so students find it easy to understand how to draw the free body diagram. As you know, in the friction lab, we have a block of wood moving over a horizontal table with a string attached to it passing over a pulley, and at the other end, you have another weight attached as shown in the diagram. So this is the block of wood, and the string passes over almost frictionless pulley, and then here is another mass attached. That's M, little m, and that's capsule. And using this arrangement and finding the acceleration of the system, we should be able to calculate the coefficient of friction between the wood and the table. Now, in order to do that, we should first draw the free body diagram. I'm just going to draw the forces acting right there. So the first force is of course the weight of that mass, mg, acting vertically down, and then you have the normal reaction acting up, vertically up, and then you have the tension acting onto the right side, the tension in the string, and then of course there is friction between the two surfaces. But when you come to the smaller mass, there are only two forces acting on it, and one is its weight, little mg, acting vertically down, and then the other one is the force of tension acting vertically up. And of course, the tension will be the same in both parts of the string. So when we try to write the equation for the bigger mass first, here are the symbols: mg, n, ft, and friction. So here it's a little mg and ft. So when you write the equation for the bigger mass first, along the y-axis, n is positive, mg is negative. So n minus mg is equal to 0. Why 0? Because there is no acceleration along the y-axis. Okay? So once you get that, you're able to make n the subject by taking mg to the other side, so it becomes n is equal to mg. Now on the x-axis, we're going to have, but before we do that, we know that the force of friction, kinetic friction in this case, is given by mu k times n, where mu k is the coefficient of kinetic friction. But n is mg, so when you substitute, you're going to get F is equal to mu k mg. All right, now on the x-axis, you have Ft positive, friction negative. So Ft minus little f is equal to ma. Now substitute for the friction. Friction is mu k mg, so substitute that value here, and you get this. So that's an important equation. So when we look at the smaller mass, there are only two forces acting. Ft is up, positive, mg is down, negative, and so the net force will be Ft minus mg, but that should be equal to negative ma. Why negative? Because the object is accelerating downwards. So for the little mass, this is the equation that we're going to get, which is Ft being positive minus mg is equal to minus ma. Again, the negative comes because the acceleration is downwards. So now we can make Ft the subject here. Taking this to the other side will make that positive, and then taking the mass as a common factor, you get this, and then plug in the value here. In place of Ft, we can write this whole thing. And when you do that, you get m g minus a minus mu sub k mg is equal to ma. So now we got to separate the mu k. So we're going to take this term to the other side, which will make it positive, and bring this over to this side, which will make it negative, right? So ma, hold on, mu kg is equal to m into, oh, that is a mistake there. So because when you take this to the other side, this is going to become negative and the other one is going to be positive. So let me change that right away. I just got that. Plus and minus, right? Is that clear enough? Right. And then the next step becomes mu k is equal to minus ma, again that minus, and then this becomes plus mg minus a whole divided by mg. So that's the equation that we're going to use to find mu k. So we can see that all that we need to do is know the masses and then find the acceleration of the system. Thank you. I hope this makes sense. And be sure to study this before you do the lab.